Hi, thanks, Ashwin. Thanks for the introduction. Good afternoon, everyone. So, as Ashwin said, today we'll be going through the through a demonstration of how you can perform, unsteady aerodynamic simulations and consequently dynamic stability analysis for aircraft and other such bodies. Um, so, the agenda is basically I'll give you a very brief overview of what SankhyaSutra Taral is and where, how, and why you can use this product. And I will take you through what dynamic stability analysis means and what the simulation workflow is to set up such a problem and simulate it with Taral. So in today's demonstration, we'll do a simulation of the role of the SACCON aircraft, like Ashwin mentioned to you. So the basic premise that you need to know is that the SankhyaSutra Taral is a lattice-Boltzmann method-based solver. What this means is that you're not actually solving the conventional Navier-Stokes equations in the macroscopic sense, but instead what you're doing is solving the mesoscopic interactions of packets of particles on a lattice that can be, as you see in the image over here on your right. So this lattice is composed of lattice cells or unit cells, and each of these unit cells has a discrete number of velocity directions assigned to it. So this discrete number of velocity directions is what governs the order of the LB model, so the lattice Boltzmann model. So the example that you see here has 27 discrete directions along the different arrows that you see. Now we basically resolve the or solve the discrete version of the Boltzmann equation on each lattice cell, and the velocity directions that we use are based on these LB models. So we have a range of different LB models that we can use, starting from this D3Q27 model, which basically means 27 discrete directions, and go all the way up to, let's say, D3Q167 for a greater number of discrete velocity directions. So the reason to use a greater number of discrete directions is basically to be able to capture higher Mach number flows and higher Reynolds number flows. So when you use SankhyaSutra Taral, because of the treatments that we do within the solver, you are guaranteed to have numerical stability without the use of turbulence models. So turbulence models are conventionally what are used when you solve the Navier-Stokes equations, or the discrete versions of the Navier-Stokes equation, because you have closure problems. And since we use a uh, cubic structure for our lattice, we also get efficient space packing. To get more details on these, you can refer to the things that I've shown you on the screen at the bottom left. So we use a number of different innovations that make our solver, push the limits of what is possible with the lattice Boltzmann method. So we use something called the entropic formulation of the lattice Boltzmann method, which basically is what defines, I mean, governs how we're able to, give you numerically stable results even at high Reynolds numbers and high Mach numbers. So one, commonly known problem with LB methods is that they're not very suitable to be applied to problems that are, beyond the incompressible limit or the strictly incompressible limit in aerodynamics. So this means it's problematic if you start using LB methods for Mach numbers of greater than 0.3 or something like that. But with our higher order models and the treatment that is coming from the entropic method, you can get good results even if you exceed this Mach number limit, so-called limit. And we also use a body-centered cubic meshing strategy instead of the simple cubic mesh, which allows us to reduce our discretization error by retaining the same number of grid points. And we also have some novel data structures and novel task decomposition methods that allow us to take complete advantage of the hardware that we run on. So our code itself is optimized to be running on a parallel architecture, something like a supercomputing cluster you guys might be familiar with. So the key benefits, I would say, of using SankhyaSutra Taral are that you are actually solving for the underlying physics without the use of turbulence models to approximate the behavior of the flow. What I mean by underlying physics is the solution of the Boltzmann equation and not an approximate solution of the Navier-Stokes equation. And in terms of the workflow, CFD is quite intensive in terms of the requirement of the mesh that you generate as well, right? So we have an automated mesh generation workflow which generates a structured grid with the possibility of having local refinements. And the process is so simple that it probably takes just a few clicks to be able to generate your mesh. You don't have to worry about inflection layers and boundary layer capturing, these kind of things. So as long as you are at a discretization level which allows you to capture the flow structures, you can be assured that you will get a good result. And we are also able to efficiently handle complex and arbitrarily moving geometries such as propellers or impellers in mixing tanks and turbine blades. And as I told you before, we are able to do quite high Reynolds numbers and high Mach numbers. So we are covering the incompressible, likely compressible, subsonic and transonic regimes using our higher order models. And with all these advantages, it makes the extension towards other multiphysics scenarios such as aeroacoustics quite easy. So I'll take you through the simulation workflow next and show you how you can import geometries or set up your case and then perform your post processing. So the simulation workflow for any CFD problem has three basic steps. The first is you pre-process your geometries and get them into a format that is accepted by the solver. And the next step is to set up your case. So this is basically provide the solver with all the inputs that it needs to be able to define your problem. And the final step is to basically simulate and then process whatever simulation data that you've generated. So SankhyaSutra Taral inherently handles the second step, so the simulation case setup step and the simulation itself. And with the graphical user interface that I'm about to show you, we also have included basic functionality to pre-process your geometry and some also detailed functionality to post-process your simulation data. So you don't have to go elsewhere with the data. CFD data can be quite large size sometimes, or it can be quite complex to post-process if you don't know exactly what you're working with. So using the GUI, it can make your life simpler by just utilizing whatever post-processing workflows are inbuilt. So in terms of pre-processing, what we expect is that the geometry that you input into the solver is basically written in the STL file format. So the STL file format is short for stereolithography, and in this format, basically your geometry is represented in the form of a surface mesh that is composed of triangular elements. So to generate this STL, you can use any third-party CAD software and generate your solid model and then convert it into an STL, or you can use something like ParaView and create basic shapes and export those as STL. What you could also do if you're adventurous is write the STL manually and then import this into the solver. So once you're ready with the STL file, you can import it, and a few checks will be done by the solver itself to ensure that the geometry is watertight and that the mesh quality is sufficient or it is satisfactory. And once this is done, you can proceed to the setup of your case. So in terms of case setup, we have four broad categories. The first is to input all the parameters that are related to grid generation. So for grid generation, what we use is something called a octree strategy. So you have the freedom to choose what kind of cell sizes you want around the geometries that you've imported. And you can also add local refinements in the form of brushes. So if, let's say, you import an airfoil into your into the solver, and you want to assign a cell size of let's say roughly 1,000 points for the chord of the airfoil, so this would be given as the patch wise resolution, and so it would be applied to the airfoil patch that you've imported. So every STL file is composed of one or more patches, and each patch basically defines one or more face, is a collection of faces of that geometry. So to apply the face-wise resolution, you apply it using the patch-wise parameter. And then for your local refinements, you can use something called brushes. So these are volumetric refinements. And your grid, since it's an octave grid, you can specify. So these patchwise and brushes will be your finer um cell sizes. And basically, to complete the grid, you can say that I want to coarsen out the grid using a certain number of levels. And since it's an octave mesh, each level will be composed of cell sizes that grow by a factor of 2. So if, let's say, you have a 1 millimeter resolution on one of your patches and you want to have 5 levels, then your coarsest level will have a cell size of 1 millimeter times 2 to the power 4. Uh, so once you're satisfied with all these inputs for the grid generation, you can move on to the definition of fluid properties and the measurements and other global settings. So I'll recap these again when I'm setting up the problem itself, in case you have had any problems following my explanations. So once you've done setting up the grid, the next thing to do is define your fluid properties. So you only need to define three basic properties: the density, kinematic viscosity, and the molar mass of your fluid. So these will be used to used by the solver to basically convert from your mesoscopic quantities into your macroscopic quantities of density, pressure, temperature, and velocities. So once you've defined your fluid, the next thing is to define your measurements. And we have four different types of measurements available, which are probes or one-dimensional point measurements. And then there are volumes, which are for saving data over a 3D region. And then there are surface measurements, which allow you to take measurements on the any surfaces that you've defined in your simulation. And the final type is the integrated forces and moments, which will give you the output of the integral of pressure over your surfaces and the moments that are generated with respect to some reference point. And for each measurement, you can define a sampling interval, which is basically the interval between the two successive writing points for that measurement. And if needed, you can define the start and end time of your measurement. And for surface measurements, you have to define the region and patch, so the STL surface to which your measurement corresponds. And once you're done with this, you can set up the initial and boundary conditions. So this will be walls, inlets, outlets, any symmetry or periodicity conditions and things like these. And you define your reference quantities through the initial conditions. So the initial condition that we support right now is for a pressure, velocity, and temperature Dirichlet conditions. And the final thing that you have to do, and this is optional, is that you set up something called restart points. So restart points basically let you save the state of your simulation at certain intervals, and whenever you have to stop the simulation and restart it, you can use the last saved point instead of starting your simulation from scratch. So this will let you save a lot of computational resources as well. So for our demonstration, like Ashwin mentioned and I mentioned earlier, we'll be using a SACCON model with a forced rolling movement. And the unsteady aerodynamics is governed by the reduced frequency, and we're using a reduced frequency of 0.05, which puts it at the border of quasi-steady and fully quasi-steady and fully unsteady flow. So dynamic stability itself is a very important criterion when you talk about aircraft design, right? A lot of the majority of your design workflow is driven by the stability of your aircraft, and basically the way you assess these dynamic and static stability is through analyzing the force and moment coefficients that are obtained by when you decompose the flow over the aircraft itself. So the dynamic stability is analyzed by assessed by analyzing the change of forces and moment coefficients with the rate of the dynamic motion. So in our case, we'll be using the roll as our dynamic motion. And each of these force coefficients or movement coefficients can be broken down into the static and dynamic components. And the forced oscillation is what lets us test and obtain this dynamic data. So we'll be using a harmonic oscillation of the aircraft along the roll axis. So the roll axis is this CMW that you are seeing here. Sorry, it's the CA axis that you're seeing here, this line here. So basically what an aircraft will be doing is oscillating on this axis about the point shown here. So it will do a pitch down and then one pitch up, go to the opposite end, and then return to its mean position. Now, the SACCON model itself is a model that was developed by the North Atlantic Treaty Organization. It's a benchmark model that is based on the concept of an unmanned combat aerial vehicle. So the model itself is a lambda wing platform. The image that you see here is of the model. So it has a 53-degree leading edge sweep angle, and the outboard design of the model is such that it delays the onset of flow separation. So the SACCON model is basically used by all design teams or solver development teams to analyze how good a solver performs. So this demonstration itself will let you, it should give you an understanding of how you can do dynamic stability analysis and how you can apply these procedures to other models that you might be working on as well. So for the unsteady setup, like I said, unsteadiness is governed by the reduced frequency, this parameter K. I'm sorry, yeah. So the reduced frequency can be computed by taking the angular frequency omega, the characteristic length b, or b by 2 is the semi-span of this aircraft, and the characteristic velocity, capital U, which for our case will be the free stream velocity. And you basically have three regimes of unsteadiness based on the reduced frequency. So if K is equal to 0, you have steady flow, which basically means that you have zero angular velocity component. And if the value of K is between 0 and 0.05, then you have quasi-steady flow behavior, which means that you will have some unsteadiness in the flow, but it will not be completely erratic. And if your unsteadiness is beyond 0.005, then your flow is going to be completely unsteady. So you will probably see all these flow features that are characteristic of sharp movements and inertia dominated flows. Like I said, we'll be using K is equal to 0.005 for our simulations. So we use the particle level set method for our rigid body motion, and this basically is an implicit function that describes the advection of an interface. So the interface is basically the interface of the STL surface and the grid that you have. And the solution is done in an Eulerian framework with marker particles evolving with a 6 degree of freedom algorithm. So this particle level set method is very well suited for 3D Cartesian grids like the one used commonly with lattice-Boltzmann methods. And it's able to resolve fast-moving boundaries with high curvatures as well, provided that your grid is sufficiently resolved. And higher order schemes can be used for smaller length scales. So if your length scale of your flow is much smaller compared to the characteristic size of your body. So for high Reynolds number cases, or if your amplitude of motion is also quite small compared to the characteristic length of your body, then this particle level set method is quite robust to be able to handle that. And the time steps size limitation due to the CFL condition is automatically handled by LBM. So even that is not a problem when it comes to level set methods, because that is usually something that is a pain point when it comes to finite volume simulations. So the CFL condition of 1 is automatically maintained by LBM, and this means that you don't have any limitations. And we will be using a multi-resolution grid strategy. So like I described to you earlier, I told you that we use an octree grid structure with different resolutions to that coarsen out. So we'll be using this coarsening out of the grid for our simulation case here. And this allows us to retain accuracy while we decrease computational cost by using only localized fine resolutions. So the SACCON model that we are using looks a bit like the image shown here on the top. So it has a root chord at the center. The root chord of the wing is close to half a meter, and the semi span is close to 0.77 meters. So we'll be simulating this model at an angle of attack of 14 degrees, and our simulation domain looks like the image I've shown you in the bottom here. So our streamwise length of the simulation domain is 6.6 meters roughly. The cross streamwise length is about 4.4 meters, and the span wise is the same, 4.4 meters. We'll be applying a no slip moving wall condition for our SACCON surface, and for all the lateral and span wise walls, we'll be using the no slip wall condition and an inlet constant velocity inlet condition for our inlet face, and a constant static pressure condition for our outlet face. We'll be using a free stream velocity of 18 meters per second. So this free stream velocity combined with the root chord of 0.479 meters gives us the Reynolds number of roughly 568,000. And we are simulating for a Mach number of 0.15. So with this, I will take you to our on-screen demonstration. One parameter that I missed to tell you is that our roll amplitude is going to be 5 degrees, and the unsteady, so the reduced frequency of 0.005 corresponds to a roll frequency of close to 0.6 hertz. So to start, say your workflow with SankhyaSutra Taral, what you can do is navigate to this URL. So our graphical user interface is a web app that you can access from any browser as in all the popular browsers. You can use Chrome, Mozilla Firefox, or Safari for iOS users. So when you register with the SankhyaSutra Taral, you will be given a set of credentials, and you can use these credentials to log into your account. So once you log into your account, you'll be shown this dashboard, and the dashboard is where you can access all your projects that you've created up until that point. As a new user, your dashboard will be empty, and the way to create a new project, you have two options. You can either create a blank project by clicking on this new project button. So it will prompt you to enter a project title. Let's say SACCON demonstration is the title I'll give my project. And you can give the project description to be something that tells you what exactly the simulation setup or the parameters are as an overview. So I will say it is a roll simulation with amplitude equal to 5 degrees and k is equal to 0.05. So once you click create project, this new project blank one gets added to your dashboard. If you don't want to create a blank project and you want to start off from a more advanced starting point, so let's say you're a new user and you don't know exactly how to navigate the system, right? So what you can do is load a template project. So if you click on the load template button, it will show you a pop-up that has all the template projects that have been created. And if you click on this save template as project link, it will give you a similar dialog box where you can enter your project title and the description, and then save this template as your own project. And once you click on the save template as project, it will appear in your dashboard. So we will go through this demonstration using a blank project that I just created. So to work on your project, you can click on this open in workspace button. Doing that will take you to the project's workspace. So each project has its own workspace where you can import or create your own geometries, set up your simulation, and then run it and do some post-processing. So we have two tabs here. The main screen tab is where you do all the setup and the imports. So let's say I want to import a geometry from my computer. So I can go click on this plus button next to geometry, and click on the import button. Or if I want to create a geometry from scratch, I can go to this create tab and create one of these basic shapes. So in our case, I'll be importing the geometry. So I click on the import button. I navigate to wherever my STL file is stored. And I selected that STL and clicked on import. So now it's showing me that it's a 6.23 MB file, and it's called SACCON 14 underscore W underscore domain. So when you import your project, you can also apply some import your geometry. You can also apply some transformations here. So we have three options. You can scale your geometry in 1, 2, or 3 directions, or you can rotate it in any of the 3 directions, and you can change the center. So basically translate your geometry by some specific mod. So all of these values, if you notice, when I was creating the project, it said it asked me for the units that my unit system that my project will be using, and you can also see it here. So I am using the SI units. So all these inputs are in meters and seconds and kilograms. So if I'm satisfied with the file that I want to import, I can click on this tick button, and it performs some pre-processing checks when you import it. And if there are any problems, it will throw a pop-up dialog box that gives you the details of the warnings or errors that it encountered. And depending on the size of the STL file that you load, it might be either instantaneously loaded or it might take a couple of moments. So the STL file that I've loaded has 7 different patches. So these 7 items are the patches that I was mentioning. So my simulation domain and the SACCON itself are made up of these patches. So if I click on one of them, it's highlighted in red here. So you know which patch you're working with. So I said that we will use a multi-resolution grid strategy. So one way to use that is by clicking on this patch and assigning a patch level resolution here. So this resolution number indicates the cell size at the in the region that is surrounding the surface highlighted in red. So let's say I want to use a patch resolution of 5 millimeters. So I will enter the number here. I enabled the set resolution radio button, and I'll click on the tick box. So the GUI now knows that I want to assign a cell size of 5 millimeters around this surface. As soon as I applied the resolution, you see that my gray box turned to blue. So for any patch that you apply a resolution, specific patch resolution, it will turn to blue here. And any patches that do not have any resolution attached to them, they will be shown as gray. So you can do this for one or more patches here. Once you've imported your geometry and set up the patch resolutions, the next thing to do is set up the regions for your simulation. So the region is basically any disjoint volume that is a part of your domain. So in our case, we have 3 such disjoint volumes. One is the volume encapsulated by the SACCON aircraft surface here. So it's internal to this surface. The second region will be whatever is external to the surface but internal to these domain walls. And the third region will be whatever is external to the domain walls. And we only want to simulate the volume which is bounded between the domain walls and the SACCON wall. So external to the SACCON wall, but internal to the domain walls. So we'll set up 3 regions. The way to set up a region is basically by telling the solver that you are defining one point that falls anywhere within that region. So for our outside region, I will say that I'm defining it with respect to this SACCON 14 with domain geometry. And I'll give it a contains coordinate of 5 comma 5 comma, let's say 10. So you were seeing probably a small yellow ball. Yeah. So this point display size, clicking on this plus and minus will make the point display size bigger. So this point, the point that you are setting with the point display size is the center of this golden or orange colored ball. So it is easier for you to identify which point exactly it is that you're setting. So I said that we don't want to simulate anything outside of the simulation domain. So we'll set it with the kind vacuum. We have two options: either set it as a vacuum type or set it as a simulate type. So since we don't want to assign any simulation points in this part of the domain, we'll say it is a vacuum type. Similarly, we'll set up the other two regions as well. So the next will be our fluid region, which is the part bounded within the domain walls and external to the SACCON. So let's say our contains coordinate is 1 comma 0 comma 0. You can verify that it is indeed where we want to place it. And I will select the kind to be simulate. And then I click the stick button and it saves my new region. So the final one will be SACCON bulk, let's say. This is the bulk of this aircraft. For this, we can define this point 0 comma 0 comma 0 is already within the bulk of the SACCON, so we can leave it at that. And I'll set this to vacuum as well. And then click the tick button. So now I have my three regions and I've assigned my patch level resolutions. The next thing you can do is set up your brushes. So like I told you, brushes are a way to control your local refinement levels. So as of now, we can define only cuboidal brushes. And the way to define the brush is by setting the min and max points of the brush. So this min and max point basically corresponds to the minimum point of the longest diagonal of this cuboid. So min point will be this and max point will be this. So let's say I want to set up a brush. I'll give the brush a name. I'll say refine 1, and maybe I'll just keep these default values. Actually, I'll extend the brush a little bit in each direction. So the extent of the brush and the resolution that you provide for this brush governs how much computational resource you'll be using. So the entire region bounded by this cuboid is going to be set with the resolution that we specify here. So this is the brush resolution. Again, if let's say I want to set this entire region with a cell size of 5 millimeters, so I can enter that value here and click on the tick button. So the entire region bounded by the cuboid that you see here is going to be filled with cells of 5 millimeter inch length. You can add any number of brushes, and you can also remove any brushes that you added by clicking on this delete button. And once you click on the delete, you'll get a pop-up message asking you whether you're sure you want to delete this, and this can't be undone. You'd have to set up the brush from scratch. So if you click cancel, it's going to retain it there. So once you're done with the brush setup, the next thing to do is add your fluid material properties. So we'll be simulating the flow of air, and we have two default properties here, air and water. So if you've selected air, you can click on this add button, and this adds the air material with these default properties to your project. Clicking on this tick button adds it to this specific project. And basically, if you click on the name or basically the material here, you can manually edit the properties as well. Let's say I want to change the density. And then if you click this, you'll get a message that the changes have been saved and you can verify it. So it changed from 1.204 to 1.14. So I'll make it 1.204 because that is the value that I need. And once you add the material, the next thing to do is apply your initial conditions. So the initial conditions should be applied always to the fluid or the simulate type regions. And the only simulate type region I have in this case is the fluid. So I'll give my initial condition an easy representative name, let's say uniform flow. I have an initial velocity of 18 meters per second in the streamwise direction, the x direction, and my temperature will be 273 Kelvin. And this is the static pressure that gets applied. So initial condition being applied to the fluid region means that all points that fall inside the fluid region will have these pressure, velocity, and temperature values. So once you're satisfied, you can click on the tick mark, and then your initial condition gets populated. So to avoid confusion or errors, we've limited users to be able to add only one initial condition per project. So if you're not sure that you want this condition to be applied, you can either edit it or you can delete the initial condition itself and then add a new one. So after adding your initial conditions, the next thing to do is apply the boundary conditions or define the boundary conditions. So the GUI has a nifty feature which automatically populates this list of boundary conditions based on the different patches that you've imported. So if you see here, this list corresponds one to one with the geometry patches that I have. So it's created one entry for each patch. And this way I don't miss defining the boundary condition for any patch. So for our SACCON wall, we'll use a SACCON surface, we'll use a moving no-slip wall condition, which is the moving wall type here. Our from to regions will be the SACCON bulk to the fluid bulk region. So the from to region defines where your boundary points are applied. So you want your boundary points to be applied on the fluid side or the simulate side of your patch. So that is why you are saying that the from region is your vacuum kind and the to region is your simulate kind. And for this surface, the pair will be SACCON bulk and fluid. And for our roll amplitude, we said we will give it an amplitude of 5 degrees. So this 5 degrees corresponds to roughly 0.087 radian. And for our angular speed of, so for the angular frequency of roughly 0.6 hertz, we get an angular speed of 3.57 radian per second. 3.757 radian per second. So once you enter the amplitude and the angular speed, the next thing to do is tell the solver how to make it rotate. So you have to define the center of rotation. So this is a point, the point about which your body will oscillate or rotate. And in our case, I leave it at 0,0,0 because I know that that is my that is the center of rotation that I want to use. And the axis of rotation is basically the normal direction or the unit normals along which your body should oscillate or rotate. So for our case, it is the x-axis. So I will say the components are 1, 0, 0. And then I save this boundary condition. So as soon as I've saved the boundary condition, this gray tick icon turns to blue. Similarly to how we saw with the patch resolution application. What you need to keep in mind is that all your boundary condition items should be blue, because only then it means that you've applied boundary conditions to all of them. So my X-min face next is my inlet face, so I'll give it the inlet condition. My from region will be outside and the to region will be fluid. And my constant velocity inlet will have a speed of 18 meters per second. So this 18 meters per second gets applied to the patch normal direction. So the surface normal direction, you can assume. So in my case, that is a free string, string-wise direction, sorry. And next I'll define my outlet. Again, outside is the from, fluid is the to, and I'm setting it to 1 atmospheric pressure outlet. So I click on the tick mark, and all my other faces I will set with, let's go with wall condition, because I want to compare my simulation data with the wind tunnel experiments. So again, from region is outside, to region is fluid, and the surface is Ymin. Since all the other three remaining walls need to be applied with the same condition, what I can do is copy my Ymin wall condition to the other three. So Ymax, Zmin, and Zmax. And once I click copy, you see that these automatically turn blue. And you can go inside and verify that they're applied correctly. So the Zmax BC has the wall condition, from region is outside, to region is fluid, and the surface is Zmax. So it's been applied correctly. So now all my surfaces have been defined with or have been assigned a boundary condition. The last thing to do then for my case setup is to define my measurements. So like I said, we have four different measurements: probes, volumes, surfaces, and integrated quantities or force and moments. Let's say I define a probe. I can choose which quantities I want to save from this list of available quantities. It's density, velocity, temperature, and pressure. Let's say I don't want to save pressure, or let's say I don't want to save temperature because I know this is very close to isothermal. So I'll disable this temperature and I'll only be saving the other three quantities. And then you give the point at which you want to save your data. And again, you have this spherical point, spherical ball to show you where your point is. You can tune the size based on how you want. This the display size does not correspond to the. I mean, if you have a bigger display ball, it does not mean that you're going to take quantities for all points enclosed by the ball. You're only going to probe at the center of this ball, only at one point. It's not going to be averaged. You should keep that in mind. So let's say I want to probe at 1,0,0, which is at the wake. So I'll reduce this. This precision parameter governs the output precision of the data that is written. So it can be so the maximum is 8. You can if you don't need such high precision, you can make it lower. So this doesn't affect the simulation in any way. It only defines the number of decimal digits that are written in your output files. Your simulation will still retain the same precision. So you can choose some integer number that you are comfortable with. And the last thing to do is specify your sampling interval or gap time. So this is the time between two successive writes. So let's say I want to save at a frequency of 1,000 hertz. So I can give a sampling interval of 1 e power minus 3 seconds. So this is 1 by 1,000. And if I want to start my measurements at some specific point and end it at some specific point, then I can enter those values as well. But in my case, I'll just start it from the starting point of the simulation. So the first iteration, and I'll let it go until the simulation runs. So I click on this tick button to apply, and I've saved this probe measurement. Oops. I think I got logged out. Yeah. So you see that even though I got logged out in the middle of my work, like my process, the last thing that I saved is already here. You can verify with the other items as well. All my boundary conditions are here. My material is there. So even if you get logged out by mistake, or if you log out in the middle of your setup, you don't have to worry that because all your information will be safely saved. Right. So the next thing I'll do is set up a volume measurement. Let's give it some name. Let's say mesh vol. And maybe I'll save only pressure and velocity for this. And this time I'll use a sampling frequency of 100 hertz. So one sample every 1/100th of a second. Click on apply, and this saved my volume measurement. And the next thing is you can save surface measurements. Similarly, sampling gap, let's say 100 hertz again in frequency. And this region is the fluid region here. So the any simulate region that is adjacent to your surface that you want to measure. So if I want to save data only on the surface of the SACCON, then I'll enable only that one. And if I want any other surfaces, then I can enable those as well. So I'll click on the stick button. So my SACCON, so data on my SACCON surface will be saved during simulation. And this integrated quantities, if you go here, these integrated force and moment measurements are available only for all the walls set with the wall condition. So to be able to save it, you enable this, and basically any wall that you set with the no slip condition will show up here. So once you're done with all this, the last thing to do is give the global parameters of your simulation. So this simulation time corresponds to the amount of physical time that you want to simulate. So let's say I want to simulate 5 seconds of flow over this SACCON aircraft. So I'll give the simulation time to be 5 seconds, and here my wall time and the number of cores correspond to the resource allocation that I want on the system where I'm performing the simulation. So if I'm using a high performance cluster, then I'll tell the cluster that I want to use 128 cores for 10 hours. So it will reserve those 128 cores for my simulation for this amount of time. Now, it is possible that your 5 seconds of simulation complete before the 10 hours are reached, or it might also happen that mm, within the 10 hours you are able to simulate only, let's say, 2 seconds or 3 seconds. So regardless of what the case is, whichever is earlier, if you complete 5 seconds, then it will automatically exit. Or if you reach 10 hours but you're not able to complete the 5 seconds, it will still exit, and you'll probably have to restart your simulation if you want to reach 5 seconds. So you should set this wall time parameter appropriately. So once you've set the wall time and the number of cores, the next thing is you set your project resolution. So this project resolution basically means the coarsest cell size that you want to use in your simulation. So for our finest cell size, we used 5 millimeters. So for let's say for our coarsest, we'll use 50 millimeters. So you can retain this value. And since it's an octree grid, octree strategy for the grid, uh, this the coarsest and the finest should be factors of multiples of factors of two of each other. So if my finest cell size is 5 millimeters, then my coarsest should be the closest power of two. Uh, so it will probably be 5 millimeters multiplied by 2 to the power 3, so which is 8. uh, what the solver will do is automatically reduce this value to 0.05, so 0.005 multiplied by 8. So even if I set it as 5 millimeters, 50 millimeters, it will choose the um, coarsest cell size appropriately. So once that is done, you can set your reference length. This reference length parameter is used to calculate your Reynolds number and report that. So it can be any arbitrary value, but you should follow whatever is the convention for your field or domain. And finally, you can set up your restart, saving your restarts. So I can either set it up in terms of the number of steps after which your simulation state should be saved, or the physical gap. So I'm simulating for 5 seconds. So let's say I want to save the state after every second of simulation. So I give a gap of 1 second. So once you're done with all this, you click on this apply, and you should get a message that that the simulation parameters have been saved successfully. And to launch your simulation or start your simulation, you click on this launch button, and it will submit your simulation job to the cluster. Or if you're running it on your local machine, it will run it there. So when you click the launch button, it will do a few checks to make sure that all the inputs that you've given make sense and are realizable. If you've missed any boundary condition definitions, or if you've not defined your initial condition, or any other uh, inputs that don't make sense, then this pre-submission check will catch those and report them, so you can go back and correct them. So if everything is okay, then you'll get a message like this. You can click on this tick button to close it. So once your simulation has started, you can access this solver log. So this is basically a log that that SankhyaSutra Taral is writing for you, which has all the details about the uh, grid, the number of points, and then what all boundary conditions have been applied, and so on. And once the discretization is done, the solver will also give you periodic messages saying that such and such number of iterations have been completed, and it took X amount of time for completing 100 iterations, and things like that. So you can monitor the progress of your simulation using this log here. What you could also do is go to the monitor plots here, Since my simulation is still in the discretization, the results have not been generated. This will be empty. But once the actual solving starts, whatever you've defined as your probe measurement, this monitor plots will have XY graphs for all the quantities that you've saved. So the y-axis will be your quantity and the x-axis will be your time. So you'll be able to monitor the physical quantities and their evolution over time as well using this monitor plots. And this solver input script is basically the Python script that is sent to the solver for simulation at the backend. So once you start your simulation, you'll be able to also get an overview of its status from this job status message here. So it's already in the running state. So it shows me running here, and once it's completed, or if it gets killed for any reason, or if you want to stop it by clicking on this stop button, then it will show the corresponding state here. So if it's finished the simulation within this wall time, it will show you completed. If the wall time is exceeded, it will show you failed and give you a message in the log. And if you've clicked on the stop, it will say stopped. So once your simulation or your solution is actually started, you might want to go to your, check your simulation data and post-process it. So you can go to the post-processing tab here and create slices, or you can visualize contours on your surface by using these item post-processing nodes here. So to create any, you can click on this plus and define all these parameters. So I've set up a case that has some post-processing already done, and I can show you these. It's for the same simulation parameters for the same case basically. So I've set up two slices. One is a slice in the y plane and one is a slice in the x plane. So depending on the size of your simulation or the size of your post-processing data, it might take a couple of moments for the slices to actually load up on your viewer. So let's say I want to visualize quantities or contours on this x slice. So my x slice is this one. So you can click on this x here and then choose the drop down to basically select the time. So this frame number at which I want the contours to be shown. So this frame number can be thought of as the time step of your simulation. So if you remember, we set up we gave the simulator the solver some gap time. So each of these frames is written after one gap time. So you can select the appropriate frame number, select the visualization or the rendering method, and you can choose the quantity that you want to visualize by clicking on this drop down. So this drop down will have all the quantities that you've saved. Yeah. Similar to this, there's also a surface post-processing that will allow you to visualize contours on the surfaces over which you've saved data. So if you remember, we saved the SACCON surface as our measurement surface. So you'll be able to visualize contours there. So in this way, you can perform the simulation of your SACCON aircraft. In our case, we did a rolling SACCON simulation. So some of the outputs that you will use for your dynamic stability analysis will be the force and moment coefficients. So what you're seeing here is some sample data that we've extracted from our previous SACCON simulation. You see that we are visualizing the role of the aircraft and the flow field that is developing over the aircraft. You'll see that there's some flow detachment here. And this graph here shows you the lift polar, and this is phase average. So why we do phase averaging is we want to average basically over the same instant at each cycle. So we have a proper representation of how the average behavior is at that point. So these the black curve shows you the lift coefficient obtained from our simulation. So we used a cell size of 1 millimeter, and we've compared it with experimental data for the the same pa- parameters that was conducted by a group at NASA. So you see that we are able to match the peak and the like max and min of our lift coefficient quite well. So you can use the lift coefficient, the drag coefficient, and the moment coefficients to analyze the static and dynamic stability of your aircraft model. I hope this was informative. We'll conclude our